Hello everyone, and thank you for watching this video. Today we're going over our second video for interview questions related to machine deep learning and data science. The second question is actually a group of several smaller questions, and I've divided them into different sections. So let's go over our first section. And if you haven't already, this section is related to a convolutional neural network, so I strongly recommend you watch one of my previous video about this topic. It could give you a much stronger background. So the question is, what are the number of parameters used in a convolutional layer? And there are two follow-up questions for this question, which could be asked either as you answer or at the beginning. The first one is, what is the difference between filters and kernels? And the other question is, when and why would you use convolutional layers over fully connected layers? Okay, so we'll start answering this. And actually, the first question and the second one are very much related one to another, because actually there's a closed form solution. There's a formula for this. And to understand the formula, you have to know the differences between filters and kernels. So let's go over one of the previous videos slides to understand the answer and the formula. Recall that what we have is some input image, let's say 3 for 3 channels and 5 by 5, which was the number of pixels that you have in that image. And then to create a convolution, what you do is you need to understand what the input channels over here, 3, and the output channels are. This determines the number of filters that you have, because you have a different filter for each one of the output channels. And each filter is comprised of 3 by 3 matrices, where each matrix is a kernel. So this is a specific kernel, the green box that we have over here, and we have 3 of them for the first filter, and we apply these 3 together over our 3 input channels to create one of the channels for the output, and we do the same thing to create the second channel. And so these are the number of parameters that we would have in this specific case, except that what isn't in this slide is the bias term, which is added into each one of them. So let's see this in the formula. The formula is the filter width, which again, it's each one of the kernels, the filter height times the number of input channels, plus 1, because each one of the filters, as again, is associated with a bias. And overall, we need to understand what the number of filters are, because this varies depending on different input and output channels. And there's also, if you watch the video, there's also a specific case for grouping of different filters. All right, moving forward to our next follow-up question. When and why would you use convolutional layers over fully connected layers? The answer to this is actually when the number of parameters exceeds too much in fully connected layers. That could be part of the answers, because what happens in fully connected layers is that each one of the neurons that you have in the next layer is connected to all of the previous either input or all of the previous layers nodes. And this could result in a large number of parameters. And so to reduce the number of parameters, you could use convolutional layers. That's, again, one part of the answer. The other part is what structure your data is. I mean, if you have spatial structure for your data, say for images, then it makes sense to convolve around with a kernel or filters and to kind of understand what the overall structure is using convolutional layers. It just makes sense. And in addition to that, which is the opposite of what I said at the beginning when fully connected, convolutional layers have much, I guess, less parameters as opposed to fully connected, because it's the same kernel, which is the parameters, it's the same filters, and all we do is that we move them around, which is what the different colors here represents. Same parameters apply to different parts of the inputs. So if you have tabular data, it could make more sense to use fully connected, and if you have spatial structure data, then it could make more sense to use convolutional layers. before we move on to the next part, if you find this video useful, please support this channel, like and subscribe. It helps me very much. And also another tip, for each one of the questions, please try to answer them, pause the video and answer them yourself before you see my answer to that question. Let's go over the next section, which is to explain statistical concepts. One is p-value and the other is central limit theorem. And I think that as a data scientist, you would probably, if ever, use them very little, because they're not really related to any applied machine deep learning applications that are used, I guess, in the industry. They could be related to theoretical concepts, but the main reason I chose to put them in this video was because after looking at different interview questions online, I see that they are asked. And well, I can understand that maybe interviewers would want you to have some theoretical background, but again, I just want to differentiate between knowing these concepts on one hand and actually using them on the other hand. So, p-value is, by definition, in hypothesis testing, measuring the probability of obtaining results as extreme as the observed ones, assuming the null hypothesis is true. Again, this is the definition. Let's try to break that into parts. Suppose we have a statistical test that we are trying to evaluate, and we have two different possible distributions. One is the null hypothesis distribution, which is this one, and the other one is, well, another distribution which could be located somewhere else. P-value by definition is the probability that you have obtained somewhat of a measure from the real null hypothesis distribution. The smaller the p-value is, the less probable that you are really evaluating something that is from the null hypothesis and probably belonging to another distribution. And what people usually do is they set some critical value. Usually it's 5%. And if we have a p-value that is lower than 5%, then that means that we have passed the test and the null hypothesis is not correct, and we have accepted the second hypothesis. The central limit theorem, again, by definition, it states that the distribution of the sample mean approaches a normal distribution as the sample size increases, regardless of the population's original distribution. This is something that we use when we sample different groups from some population, say, people heights. So we sample them from the population, and as the sample size increases, the central limit theorem states that if we take the mean of all of these groups, then the mean values that we obtain are distributed normally. And the reason that this is an important sentence or a theorem is because it allows us to use normal distribution assumptions on many types of data, even if the population's original distribution is not really a normal distribution. The mean sample distribution does approach a normal distribution. Okay, and moving on to the next part of our interview question, explain either over or underfitting and the bias variance trade-off, which I guess would be the most basic question that you could be asked in a data science interview. And the other one is, how would you handle missing data in a data set, which is also a very basic question. So let's start with the first one. So overfitting and underfitting. Overfitting is when the model fits itself into the training data too much, and while there's good performance on the training data, that leads to poor performance on the test data. Underfitting is when the model doesn't fit itself to the training data, and that leads to poor performance both on the training data and the test data. And the bias variance trade-off is, it's very much related to over and underfitting, but it's not, there could be more reasons I'll explain more. So high variance is when the model is too complex, and when the model is too complex and fits itself into the data too much, that could lead to overfitting. But that isn't the only reason that a model can overfit. It can overfit because maybe the number of input dimension is too big. That's also a reason for overfitting. High bias is when the model is simply too simple, and again, that could lead to underfitting. But again, that's not the only reason. Another reason would be maybe you haven't trained the model enough, and if you would have continued to train the model, then there wouldn't be underfitting. High bias is when, by definition, the model is too simple. And in the bias variance trade-off, the goal is to find the good trade-off between the right balance between the two. And there's a good illustration of this in the next slide. So suppose that the orange squares over here is our data. And on the left, what we have is a line trying to fit itself into the data, but it doesn't have enough complexity, so we result in underfitting. There's bad performance on, well, all types of data, both training and tests. Even though we don't see the difference between training and tests, it's bad. And on the other side, we have a large variance for the model. So while it does fit some specific points, which I presume are the training data, it has almost, I guess, zero error when we try to address these points. It would perform poorly on the test data points. And again, like we said in the previous slide, the goal is to find the right complexity for the model to fit itself into the data. Moving on to the last, I guess, question. How would you handle missing data in a data set? And there are many answers to this question. One is to simply drop the missing values. If you have only a few missing values, you could simply drop them, drop the rows or the corresponding rows or columns. And if you don't lose too much data, then this is an applicable solution. Another way to handle missing data is imputation. You can, for numerical data, use either the mean or the median to fill in the gaps. Or for categorical data, you could use the most frequent value. And again, that fills in the gaps for the missing data. You can also predict what you would expect in specific samples by using some machine learning models like KNN for imputation to fill in the gaps and estimate what values are missing. Another is to use some special categories. So suppose you have many missing values and you don't want to drop the missing values because you would lose too much data. You can assign a unique value like unknown for categorical values, or 0 or -1 for numerical values. And well, this would be a good idea, especially if you have patterns. Suppose for a specific class, one feature is almost always missing. So you don't want to miss that entire class. You don't want to drop all of the samples associated with these class. What you want to do is to check that pattern, investigate whether there's a reason for that. Maybe it was because the way the data was sampled, and of course you can use these types of methods to fill in the gaps. So thank you again for watching this video. I hope it helps you a lot. Let me know in the comments below if I can make a video on anything else. And again, please like and subscribe.